In this talk, I'm going to propose a new principle, which I call it the broken mirror principle of quantum mechanics. And it is related to the idea of Yakir's approach to quantum mechanics. Now, first, I want to start with saying Mazal Tov, Yakir, congratulations. And as you can see, I think this is a famous picture of Yakir. Here Yakir is in his office at home in Israel, near the chessboard. At almost every meeting that we have, we play chess together near the wall of fame, which is here, essentially. And it contains all of his awards and prizes, together with the National Medal of Science, awarded by President Barack Obama. And for you maybe, you take this frame, but for me, this frame is very common. A lot of times when you play chess, don't ask me who commonly win the game. Yakir, of course. And so let us start. When we think about quantum mechanics, essentially the standard formalism of quantum mechanics goes like the Schrödinger equation. And from the Schrödinger picture, when we think about the particles as quantum states in Hilbert space, as waves, we have this intuition that we studied at our degrees, right? And one of the concepts that Yakir holds when you do his research is to consider the two-state vector formalism, right? Which means that we consider pre- and post-selected states as a full description of the particle. Quantum mechanics tells us that this mirror of quantum mechanics is broke. It is broke in the sense that we have this sort of pieces which give us different reformulations, different interpretations of the quantum system, of the particle itself. For example, we can have the Heisenberg picture. We can have the two-state vector formalism, Schrödinger picture, stochastic mechanics of Edward Nelson, and many different types of reformulations. Now, this presentation, it is more about the concept that I'm going to show you, with focusing on the Madelung equations, which is a reformulation of the Schrödinger equation in the form of virtual fluid, considering the particle as a virtual fluid. And essentially, what is the broken mirror principle that I propose? Yakir thought about saying, okay, we have this two-state vector formalism, and how we can gain from this formalism new quantum phenomena. But essentially, this quantum phenomena is independent from the reformulation. They hold by themselves. So the proposed principles say the following. Choose a suitable reformulation of quantum mechanics for discovering novel quantum phenomena. But what about these quantum phenomena? That they are independent of the specific interpretation of quantum mechanics. They hold by themselves. So you can think about it, I have this broken mirror, how can I take a piece? Maybe it will help me to discover a new insight about quantum mechanics that is independent from this specific reformulation. So in the Madelung picture, we consider the following polar representation of the wave function. And here we have this radial part where rho is the density function of the particle. In this description, I consider x and t. The wave function is a function of the spatial dimensions and time. And we have this phase. Now, if we are talking about history, if we will talk about history, only a year after Schrödinger proposed his famous master equation, Erwin Madelung, the same initial name, proposed the Madelung picture by saying that I can take the Schrödinger equation and decompose it into a system of coupled equations. What is interesting about these equations? Let's see. So suppose we have this Hamiltonian, and I take, as Madelung told us, I can take this polar representation. Consider the Schrödinger equation, and you put this psi. Essentially what you get, it's real part of the equation, and it's imaginary one. The real part takes this form, okay? Essentially, this is the Hamilton-Jacobi equation. This is the classic Hamilton-Jacobi equation with a particular addition, which is Q rho. Now we say that Q, it is the Bohm's potential. And here, this is the continuity equation, which must come because rho, it's a density function. So essentially, without this Q, we have a system of a classical fluid. And with this Q, we said, OK, we have this Q, and now it is called the quantum Hamilton-Jacobi equation of the particle described by a virtual fluid, described by these coupled equations. This is the idea of Madelung when he proposed is formalism. And Q takes this form. Essentially, Bohm's, he said that this description is the self-organizing process of the quantum system. Now, it takes the form of the curvature, you can say the curvature of the radial part divided by the radial part. He also called it normalized curvature. And notice that from these equations, what depends on H Planck, H Planck comes only through the quantum potential, and when H bar goes to 0, we obtain classical Hamilton-Jacobi equation. So really, this gives you, the Q gives you the insight about quantum mechanics. There is another argument that it gives you the concept of non-locality, because you have here description of second derivative of the radial part. Okay? I don't want to get into it, but if you will ask me, I will tell you later. Now, how can we exploit this reformulation? And remember, what I'm going to show you now, it's only based on the Madelung picture. Okay, there are different types of reformulations that we can gain from them, different new phenomena that are independent from the specific reformulation of the quantum system. So the first thing that I'm going to discuss is the idea of countering fundamental forces in nature using the internal potential of the system, which is the potential that belongs to the particle itself. Now, before that, I just want to say that in the recent years, there is a hot topic about how we can engineer the wave function into specific forms, structured wave functions. Essentially, with electrons, if I remember correctly, people do that, and there are a lot of experiments with considering electrons and other such particles. However, when we think about more complicated particles like atoms, things are more complicated, but on theory, it may be work in the future. Okay, so now what I'm going to deal is that the idea of having specific form of wave function that will help me to achieve new phenomena. Okay, so let us start with the first concept. So we go back to the idea of the Madelung equations, and just notice this is total potential of the system, right? Q plus V. There is a paper published this year by me and colleagues, also Eli Cohen, which is in this conference. And we talked about how we can counter a fundamental law of attraction. Essentially, we talked about different kinds of potentials, but giving attention to the Casimir-Polder force, and how we can counter it using engineering of the quantum wave packet. So we have this part, right, of the equation, of the system of coupled equations. By saying that we want to counter this potential, we just want to ask ourselves the following. What specific form of Q will cancel out V? So we simply take Q plus V equals to 0, which gives me this equation that I have to solve. Now,
the cancellation would be static for all times or just for one particular moment?
This is a very, very good question, and I'll talk about it. It is time dependent.
So
yeah.
it will be cancelled for an instant.
Yeah, it can be counted for a long time. You just need to do, there is a question about sensitivity and how you can do this specific form of the solution. And even the solution itself, I'm going to show, is not perfect, and we need to modify it. So we ran some empirical simulations to see how really the solution gives us.
To solve the equation that you given,
Mm-hmm.
get the solution. Will it hold for all time?
All time.
It will hold for
Yeah,
all time.
yeah, yeah. Now we have the Casimir-Polder effect. Essentially, in the Casimir-Polder potential, it is more involved than simply this form. But we consider this simplistic form, I consider it here, but in the paper we considered the more complicated form of the Casimir-Polder effect, potential. But we can take this form where we consider that the particle is very close to the surface, to the dielectric surface. By the way, the Casimir-Polder effect is slightly different than the Casimir effect, which talks about two plates that goes together. Months after he published the paper, they published this concept of having a neutral atom that is attracted to a dielectric surface, which is the Casimir-Polder effect. Okay. Now, I just want to just say that this C, it depends, this constant C depends on the surface itself and the atoms. Okay, so it's slightly complicated how we can infer it from the exact type of surface and atom. Essentially, when we do this equation that we have this equation, and we solved it, and this is the solution. But what is the problem with this solution? So first thing, we need to understand that this solution that we got can have negative values. But it is okay, because we consider the density function. And here this is the radial part, so it can be negative, and the density, it's regular, it's okay. It is positive. But what is the big problem with this solution?
Sorry, did you assume some specific external potential?
Yeah, this potential. Yeah,
Okay,
that's all.
So I'm trying to understand the logic and where you're going to. You have a specific potential, and you want to have some additional time-dependent potential that will cancel.
No, this will be trivial. I want to exploit the Madelung equation. What Madelung, the picture, says to me is says that the total potential in the system, it's the internal potential, which depends on the particle, on the amplitude of the particle. The total potential is Q plus V. V is the external potential. Q, it's Bohm's potential with this form. I want to use a specific form of the amplitude. This is the amplitude, square root of rho. Specific form of R such that I will have this. It will cancel this specific form of the amplitude will cancel out the potential itself. It's not an external potential, it's the internal potential, according to Madelung.
So suppose that you found what would be the consequence? So, you know, the potential is attractive, so the particle cannot get to infinity. Now, is what you're saying that you can engineer a wave function that will take it out of this trap? Because if that's the point, then anything that has energy, anything that has a positive energy will not be trapped, right?
Mm-hmm.
Because the potential is negative. If the total energy will be positive, then the particle will not be trapped.
Mm-hmm.
So is this what you're doing?
What I'm doing is that I want to cancel the external potential. So I'll have this kind of, you can think about it as a levitation. Just want to get rid from the attraction force. That's all. With a specific form of the amplitude of the wave function.
But will the particle escape to infinity?
No.
So where will it be?
So let's see. So the solution, it has this problem that it is not in L2. Like we need it to be normalizable. So we have this problem that it is not square integrable. So square integrable, it is not. So we said, okay, not good. We want to modify it. So we just added to it a Gaussian part. This is.
Go back just back to that
Yeah.
previous slide. So you're saying it can't take negative values?
Can you speak to the microphone? Sorry.
Yeah. So you're saying it can't take.
It can.
It can take negative
Because
values.
rho,
I mean,
it's
yeah,
okay.
I can see that in there can take negative values. I thought you were saying that there's some sort of constraint.
No.
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 Okay.
This is not a solution. When I added the Gaussian, it's not a solution. It's like shifted from the solution because I said, okay, we said, okay, let's not talk about this form because it's not so cool. It's not square integrable. Let us add a Gaussian part and see how this modification of the solution give us maybe a good cancellation of the potential. Now, as I said, in this talk, unfortunately, I'm not going to talk about the specific details. I will be happy to do so at the dinner. So this is one concept. And then we did the analysis and considered specific atoms, like rubidium 87, and considered such situations, how we can counter the Casimir-Polder effect with the idea of maybe, and this idea is also been studied by Michael Berry, if I'm correct, with countering the gravity force. Okay, by using engineered wave function.
So he was using like C over R squared rather than, or C over
Yeah,
G squared
yeah,
rather
yeah,
than
yeah.
C to the fourth.
Yeah. The solution of this will be a airy function which counters gravity. So it's self-acceleration in the opposite direction of the gravity. Okay, another idea is that to consider a vanished quantum potential.
So if you finish with this, I still
Yeah.
have
Okay.
a picture.
Mm-hmm.
You have a static potential, and you can in principle solve it for eigenfunctions. And then you can construct a wave function which is a superposition of eigenfunctions. So this is standard quantum mechanics. What are you saying beyond this?
So what I'm saying is that I want to find a specific form of the amplitude that cancels out the potential.
If you take the solution, an eigenstate with zero energy,
Mm-hmm.
exactly zero energy, the potential is negative, so you cancel it.
Mm-hmm.
So why not just take, so is this just
But here I consider wave packets. You say you are talking about a specific eigen
Yeah, take
solution.
magnitude.
No, I consider wave packets.
You consider
Wave packets.
wave? Well, an eigenstate is a.
Hmm.
If you want something that doesn't have a dynamics, then it needs to be an eigenstate. If it's a wave
It will
packet,
have
you know,
dynamics, yeah, and
states it will have dynamics.
sure, we studied it.
So what's the definition of the problem? Are we trying to find something that has no dynamics or something that has dynamics?
We want to consider the wave packets, and they will change over time, and we want to see how much time it will cancel out until it really will be in the form that the Casimir-Poldel effect will overcome it.
So if you want to see how long it will take before the wave packet that you created dispersed or something? And where do we see that in this?
Yeah, I didn't put it here. I just want to talk about points, different concepts that maybe we can exploit the Madlong equations for taking these new insights, because I'm not sure that I can see this insight using the Schrödinger picture, because here I just consider the amplitude. It comes from the quantum potential itself. That's all.
Now this psi is the wave function, is the
Yeah,
Schrödinger wave.
yeah.
In this case, it's a real function.
Yeah.
Just square it will be.
So Howard has a question as well.
Yeah, so why, I don't understand why you're starting with this particular potential, this Casimir-Poldel potential or whatever, because are you trying to cancel the quantum potential but
No,
keep
I don't
some
want to. No, I want to exploit the quantum potential to use it in order to cancel out the external potential. I don't want to cancel the internal potential, the Bohm's potential. I want to use the Bohm's potential to use it. Bohm's potential tells me what the specific form of the amplitude should be for canceling out the external potential. This is what I care about.
Okay, but then you should have the classical motion of a free particle.
We will talk about it.
But I think that I think it's just the difference between seeing things in terms of the Schrödinger equation as opposed to seeing this Madelung rewriting of that equation, right?
Yeah.
So you're not saying that I'm not allowed to take the Schrödinger equation?
No,
So
of course you are allowed.
what you're describing to us may boil down to having a static potential, solving for the eigenfunctions, preparing some initial wave packet, and following the evolution or the dispersion of this wave packet in this potential. And now, given this, you want to describe it in a different language.
Yeah, there is nothing unordinary in the quantum system. I don't try to say I'm in favor of this one or that one. Just see it differently, that's all. Now I want to talk about classicality of single particles. Essentially, with single particles, we don't really can have classical mechanics. But if we consider this Madelung equations, in principle, we can ask in what case the quantum potential vanishes for single particles. And when it is vanished, it means that we still have quantum behavior, but the quantum behavior will follow a classical fluid, virtual fluid, which is the classical Hamilton-Jacobi equations when Q is 0 and the continuity equation. So let me go to the next idea. I know that it is short. The talk also will be shorter than previous talks, I think. And I think people are hungry, so let us continue. Let us talk about the following idea. We have a particle, a single particle, in heterostructure. What is the meaning of heterostructure? When the particle is in this heterostructure, it has a position, spatial dependent effective mass, mu x. Another problem. There is another problem. And this is the Schrödinger equation of that problem. This is well known and well studied. Let us consider the Madelung reformulation, which is this polar representation. We can do that anytime. In our case, and we get, again, a modified version of the equations of motion, but still, we have here the quantum potential and V.
Is there an advantage of writing as a square root of rho?
No. I didn't have a lot of time to write the presentation, so sorry about the symbols. When Madelung proposed his reformulation and the Bohm saw this quantum potential, which is also connected to the pilot wave, essentially what he saw is that the quantum potential, it's a normalized curvature of the amplitude. Here it is not like that. Here, because we have spatial dependent effective mass, position dependent effective mass, this is the quantum potential that we have, which is, yes, it is a normalized curvature of the amplitude, but yes, this addition, we have this addition, which is this thing that depends also on mu and the same derivative order than the amplitude itself. We'll see what does it mean. But this is the modified version of the quantum potential when we have position dependent effective mass. By the way, it is also related to the, I don't want to go there because I'm not an expert in that field, but it is also related to electrons in semiconductor retrostructures. I saw papers that deals with this idea that position-dependent effective mass that we have. Now,
There's also equivalent in optics. The Eikonel equation also has this Laplacian over rho effect in it, but it's always thrown out because it's much smaller than k naught squared. So
yeah,
anyway,
interesting.
There's a similar thing.
Interesting. Here, I just want to say, okay, what about vanishing Q? Like finding the suitable amplitude for having a vanished quantum potential. If I'm not wrong, as you saw in the standard quantum system, maybe it is trivial, tell me if I'm wrong, to take Q equals to 0 when it is simply normalized amplitude, normalized curvature of the amplitude. But here we have a non-standard quantum system, and we have a non-standard problem with saying that now let us consider the vanishing quantum potential. Okay? This will give us some hint for classical behavior in the sense that now the equations of motion will take the form of a classical fluid, virtual fluid. So essentially this equation boils down to this equation, elliptic partial differential equation that we need to solve. Mu is known. The position-dependent effectiveness is known. Depends on the heterostructure itself. So for a specific example, we can consider mu in this form, which is a well-used form, and consider that x is between 0 and L. We have this kind of a walls, potential well. For this problem, with a class of potentials, it has been well studied, it's not new here. The eigen solutions take this form. This is the eigen solution. So you can see that psi n at point 0 equals to psi n at point L equals to 0. So it really lives in that area, between 0 and L. Okay, and this is the energy levels. Remember this equation? So now we consider one-dimensional problem, right? In this case, the suitable amplitude that will solve our equation will take this form. But again, this form, it's not, first of all, we don't care, it's only on this finite potential well, right? So it is okay about this square integrability L2 that I talked about. But the boundary conditions are not fulfilled in this example. But notice that what this form is the same here, just multiplied by sine. So we can multiply it by sine, again having this modified solution that we want to have, but this is essentially an eigen solution, okay? So nothing's new here, just so that the solution we can modify it to be in one of the eigen solutions, which is good. We like eigen solutions. And in that case, we have vanished quantum potential this area, then it goes, this is an example. Then it goes like that, and not nice, but here we have this quantum potential. For this example, it's like saying I did nothing. I just had this observation and just said, okay, for this specific problem, if I take the eigenfunction, the first eigen solution, I will have vanished potential almost everywhere, okay? But more than that, I don't want to go there. More than that, when I had this modified version of the quantum potential with this kappa, it is the form of the standard quantum potential, which is the normalized curvature of the amplitude. With this addition, I can have situations also where this, the Q quantum potential B mod, is overcome the curvature, the normalized curvature. And in that case, for example, I can have that the quantum potential will follow QB, okay, the additional part, and not the curvature. You can ask, okay, so, but in every standard quantum system, we can see the behavior, the essence, the structure of the quantum system has come from the quantum potential in the Madung picture. It is directly related to the curvature of the wave function. And here in this non-standard quantum system, we can see that maybe the behavior will follow the structure of this self-organizing process of the system. The quantum potential is followed by the surface, by this heterostructure. Okay, for example, it can also be, I don't want to go there now, but it can be a curved space time in general idea. So, so this is only an observation about this modified quantum potential. Let us consider a different problem, and this is how it goes. Just give you some hints about the broken mirror principle with the idea of the Madung equations. If you consider the case of the Klein-Gordon equation in curved space-time, we have this form, well-known form. G is the metric, space-time metric, gamma Christoffel symbols. Now, again, let's do the polar representation. We do that. We have these coupled equations of motion. And now this is what we have. Here, the quantum potential is like that. And the second one is the for current conservation, this equation. Much similar to before, we can ask, okay, what specific amplitude, specific form of amplitude will give me vanished quantum potential? What it will be? But instead, we can ask other thing. The quantum potential, as Bohm thought about it, he also discussed it as some kind of information that comes, some kind of potential of information. So here, we can, instead of saying, let's take Q equals to 0, we can say we have the quantum force, FQ, which is, this is the definition of Bohm, derivative of Q, and we want the quantum force to be 0. This means that the equation that we eager and want to, it's Q quantum potential plus some constant equals to 0. This means that the quantum potential is a constant, zero information about the system, zero quantum force. Okay, so this is the thing. But I want to cheat or not to cheat. It depends how you see that. Q, quantum potential, it's in units of energy. Lambda should also be units of energy. Let me define lambda as m, sum of m effective, okay? This other problem, right? It's not position dependent effective, other thing. Let us consider this form as a m sum effective squared, c squared, c the speed of light. So this is lambda, some constant. When I do that, I get that the desired equation that needs to be solved is this for the amplitude. What is it? Essentially, this is the same Klein-Gordon equation in the same curved space time G. But now, the desired solution for the amplitude is for the same problem, but with some effective mass. And if we solve it and find the amplitude, we find our vanished quantum potential that we can analyze. In the first example, I considered some specific V. I took, for example, here the Casimir polder. But for this, I just want to say, okay, I have a solution. You see, it's without any potential. It's the problem of Klein-Gordon, only in curved space, empty curved space-time. And I can find suitable. For this, I can say, okay, I have a solution R, but is it true that R is a solution of the amplitude solution of my original problem, my original equation? Of course not for arbitrary potential. But we can find suitable potential V star such that R, the solution of this, will really be a solution of the problem itself. Okay? How you can engineer this V star and all this stuff, we can talk about it later. But we can find a potential that gives us a solution in the form of R, the desired R. Last thing, not more than that, and I will not fully discuss it. But just want to say that if we consider the Schrödinger equation, one second, and couple it to a heat equation for the density function, and say again, okay, let's think about the Madron picture. And notice that the curvature that I talked about can take this form. The curvature, you can take this form. Yeah, I just want to have a Schrödinger equation and couple the density function with the heat equation.
So you have the upper equation is Schrödinger equation.
Yeah.
And psi is the wave function. Second equation, rho is an independent variable?
No, it's a density function. It's psi. Yeah.
So you have two equations for a single unknown, no?
No, I want to find psi such that this is followed.
You want to find a psi that will solve both?
Yeah, that's all.
And maybe there is.
Yeah, exactly. But just small insight, I don't want to go there, but just small insight, if you do the Madron equations, you will see that it will take this form. So kappa, it's the curvature, the normalized curvature amplitudes. So this form, I suggest, say that this is the equation of motion. This is the original quantum Hamilton-Jacobi equation, which may imply that the dynamics of the particle is simply governed by kappa, by the curvature, for this case. Okay? So what I just wanted to say is that we can see things differently with talking about different pictures. Okay? And Yakir did a lot about the two-state vector formalism and got very exciting results with talking about two-state vector formalism. Now here, just want to take this small piece of glass, maybe the modern equation, and think about it as a new perspective on quantum mechanics. Now, Yakir, Einstein was the non-official mentor of Bohm, and Yakir is my non-official mentor. Yakir, thank you for all these years that you have taught me what I wanted to achieve most, which is to capture nature's beauty through science. And I just want to say something. I once asked Yakir how he came up with all of his brilliant ideas. For a moment, he was silenced, but then he simply told me the story about Columbus egg. Thank you.
Questions? What was the last word you said?
What?
Story of what?
Columbus egg.
What?
Columbus egg. You don't know the story about Columbus egg? Really? In America? Okay, so people told Columbus it was not so brilliant to think, okay, you took a boat and came to America. But not so sophisticated, but he took an egg after boiling it, and then he said to them, who know how to make it up without falling? People have not succeeded in that. He just took the egg, put like that, broke it down, now it stands.
No.
So tell us, Yakir, tell us.
No, I think you cooked it. You boiled it.
Yeah, I said it, he boiled it.
Oh, I did it.
Yeah, if not, you can do omelet with it. Yeah, he boiled it. So the idea of thinking outside of the box, but not only saying that, really think it. This is the main problem or a goal that we need to have. That's all. Thank you all.